Hello, everybody. Welcome to the online version of Chapter 12, where today we're going to look at z-tests and single sample t-tests. And so let's go ahead and begin. We will begin with a question. Now, instead of a clicker question, I'll show you this question on my screen. I want you to take a look at this and tell me which of the following is false. So the correct answer to this is A. Standard deviation between a population and a sample is slightly different because the standard deviation for a population is based off of a variance, remember variance, that's n minus 1. So we are looking at A. A is the correct answer. The standard deviation for a population, that's the lowercase sigma that you see right there, that is going to take the sum of squares divided by n, and then you want to take the square root of that. So the variance is sum of squares divided by n, and then you take the square root of that to get the standard deviation. However, S, that's the standard deviation for a sample, you are just going to do sum of squares divided by n minus 1. And then you take the square root of that in order to find the standard deviation. So A is the correct answer. So in selection B, mu and x bar, they're calculated the same way. Mu is for a population, and so is lowercase sigma. So the correct answer for this one is A as a review. Now, let's talk about what we're discussing today. We are now moving away from ideas of correlation, and now we're getting into comparing means. So what we're really going to get into for the next little while when we get into z-tests, but all kinds of t-tests. So we have a few chapters of t-tests coming up. Each one of those is looking at one group compared to another group. And when we mean that is we're looking at the mean compared to another mean. Now, it's not just looking is the mean different than the other mean. It's using some other ideas of variance in order to see, are they really different from each other? And when we're looking at a z-test or a t-test, we use a z-test or what's called a single sample t-test. There's other kinds of t-tests that are coming up. We're going to have paired samples t-tests and independent samples t-tests, but when we talk about a single samples t-test, what we're doing is we're comparing a mean for our sample compared to the population's mean. For a z-test and a t-test, a single samples t-test, we're going to compare our sample's mean to the population's mean. The test is to see if those are significantly different from each other. So that's what we're doing in this chapter. We use a z-test when we know mu and lowercase sigma. That is, when we know the population's mean and the population's standard deviation. We have to know both of those. For a z-test, in order to use a z-test, we have to know both of those, the mu and the lowercase sigma, the mean of the population and the standard deviation of the population. You have to know both of those things. Okay, now we need to talk about ideas of a different kind of standard deviation. Specifically, what we're talking about is a standard deviation for the mean. Up until now, we've talked about z-scores for one person, okay? A z-score has always been one person's individual score compared to the rest of the group. But now we're not talking about that anymore. We're talking about the idea of our sample, right? So it's actually the mean of means. So mu sub x bar is what we're discussing here. It's the mean of the possible means that could be there, okay? And so mu sub x bar is what we're going to use for a z-test. Now, lucky for us, that's the same as mu. It is the same thing. So the mean for a sample, a mean for the population is the same as the mean of all the possible means of a population. That's what that's saying. But the same is not necessarily true for the standard deviation. So the standard deviation, that's the lowercase sigma sub x bar, is actually going to be sigma divided by the square root of n. Now this again is an idea of using this to compare for the means. What we're really doing here is we're not looking for just the mean of the population. We're looking for the mean of all the possible means of a population. And I know that sounds a little bit confusing, but that's really what's going on. And so we're going to use the same formula for a z-score, except that now we're talking about means. we're going to change the standard deviation. Okay, this sigma right here, we're going to do sigma sub x bar, which is the population standard deviation divided by the square root of n. The reason why this is important is because of this particular formula right here. We are now going to calculate a z-score. But remember, we're not talking about a z-score for an individual. That's the normal z. We're now looking for a z-score for the sample, right? So we're comparing our sample to the whole population. That's why we call this a z sub OBT, a z obtained. To get the z obtained, we're talking about the z-score for the whole sample. And that means then we need to get the mean of the sample minus the mean of the population, which is what we've been talking about before, divided by the standard deviation of the means. That is the population standard deviation of all possible means. So in this particular case, remember, we're talking about, instead of x minus x bar divided by s, which is the standard deviation, we're now looking for the mean of our sample, that's the x bar obtained, minus the population's mean, divided by the standard deviation of the means, which is the normal lowercase sigma, okay, the standard deviation of the population, divided by the square root of n. So what we're seeing right here, it looks very similar to a z-score for one individual, but now we're looking for the z-score for the whole sample. So we're looking at x bar minus mu divided by sigma sub x bar. And sigma sub x bar is sigma divided by the square root of n. So let's try it out. I know that the mean SAT score for the United States is 1060 with a standard deviation of 195. If that's the case, then I can be able to figure out if my group, my sample, has a significantly different SAT score from the whole population. The reason why you do this is to see if, if some group is different. So let's say, for example, that we had a high school that we were looking at. And this individual high school has been having, we want to see if the high school students in this high school are doing significantly worse on the SAT compared to the whole population. Let's say it's in a underprivileged community or something like that, right? So what we would do is we would take the mean for the entire United States, which is 1060, and the standard deviation, which is 195, and we get the mean for our high school. We'd also have to know how many people are in that mean, because we're going to need to do the square root of n. And then we can figure out whether or not this high school is significantly different from the population, from everybody else. So let's do this with CU Bowler students. Let's say the opposite way. Let's say I think that CU Bowler students are more prepared for college than the rest of the United States. So I sample 16 CU Bowler students. Okay, my N is 16. The mean that I got for these CU Bowler students just in my sample was 1260. So what we're going to do is we're going to go back and we're going to use this. Okay, X bar obtained is the mean of my sample. That is 1260. The mean SAT for my students, our sample is 1260. Mu is the population mean. It's right here. So the mean for the whole population of the United States is 1060. Sigma sub x bar is the population standard deviation divided by the square root of n. So it is 195, because that's the standard deviation for the population, divided by the square root of 16. Go ahead and work on that right now. Okay, once we get that score, we have to find the critical value. We do this the same way we do this as any other time, right? Because we're looking at a z-score, we're going to use the z-table, which is the normal distribution. So just like we've done it in future times, we're going to look at the normal distribution. So let's say in this particular case that let's do a one-tailed test, just for fun. A one-tailed test. So that means that I think that CU Boulder students can only have higher SAT scores in the population, and alpha equals 0.05. So figure out whether or not we're going to reject or fail to reject the null hypothesis. Okay, so far we've talked about a z-test. Now we're going to talk about a single sample t-test. Many times when you're doing this, I'm looking at my group compared to the rest of the population. I might know the population's mean, but I often don't know the population's standard deviation. You use a single sample t-test when you know mu, but you don't know sigma. That is, you know the population's mean, but you don't know the population's standard deviation. It's the same basic process. It's exactly the same idea as the z-test, except now instead of using the standard deviation from the population, we're going to use the standard deviation from the sample, and we're going to estimate the standard deviation from the sample as being the standard deviation for the population. We call this the standard deviation sub x bar, or the standard deviation of the mean. And just like we did sigma divided by the square root of n, now we're going to do s, which is the standard deviation of the sample, divided by the square root of n. Same process, and that gives us this t statistic. So look at the similarity between the z statistic and the t statistic. Now remember, it's not a normal z-score that we were talking about before, because now we're talking about a z-score for the mean, right? In this case, we're looking at a t-test of the mean. So we get the mean minus mu divided by the standard deviation of the means, which in this case is the sample's standard deviation divided by the square root of n. We use t when we don't have the population's standard deviation. We use z when we know both the population's mean and the population's standard deviation. So now let's do this in a different problem. I think that CU Boulder students commute less time than the population. All right. I know that the mean commute time for the population is 25.4 minutes. By the way, these numbers are real. Those are actual SAT scores and actual commute times. That is the real average commute time in the United States. So what we're looking for now is we've got this new group, CU Boulder students. I want to see if CU Boulder students commute less than the general population. So the way I do this is the same way I've done it before. Look at the mean. Idea is that same central tendency mean that we've talked about before. So I get the mean, that is the sum of everything divided by n, same as we've always done it, right? And then I'm going to subtract that from the population's mean. So my sample's mean minus the population's mean divided by the standard deviation of the sample divided by the square root of n. So let me get back to this. So in this particular case, let's pretend that the standard deviation of my sample is 4, and the average commute time for my CU Boulder students is 20 minutes. So in this case, my sample's mean is 20, the population's mean is 25.4, the standard deviation is 4, and in this case, the sample that I had 9 people in my sample. So try that out. See what you get for your answer.